In this video, we are going to find the expected number of positive peaks of a signal. So let's make a sketch, and therefore from the sketch you will understand way better than with words. So for example, let's sketch a signal like this. It is just a sketch, so please do not expect too much of the sketch. But now we have the following signal x of t. Here we have time t, and at time t1 we will have a maximum. Then at time t2 we will have another maximum. At time t3 another maximum, and so on and so forth. So this signal here, x of t, in general will be stochastic, a random signal. So I will put a tilde under it in order to highlight the fact that it is a random signal. So in general, a random signal might exhibit maxima and minima at different locations because of the randomness of the signal. So let's put tildes also here for t1, t2, and t3. So it means that these maxima in general might have a different location depending on the randomness of the signal. One realization of the signal might be this one, but then we might have other different realizations of the same signal because it is simply a random process. And now what I'm going to consider is I'm going to consider the derivative of the signal, like x prime of t by definition will be the derivative with respect to time of the signal x of t. And let's take the step function that I will call u, and let's consider the step function of x prime of t. So it means that this function here will be equal to 1 when x prime is greater than 0, and it will be 0 when x prime is negative. So for example, here from 0 to t1, let's draw two vertical lines. Well, this function will be equal to 1 here because x is increasing, and if it is increasing, it means that x prime is greater than 0. So u will be equal to 1 here. It will be 0 over this interval here because the function was decreasing until we reach this minimum. Then it is increasing up to the other maximum at t equal to t2. So here we will have that the function u is equal to 1. And of course you get the idea. Here will be equal to 0. Then from this point to t3 it will be 1. Then it will decrease here, and so on and so forth. Now this is quite useful to be able to count the number of maxima and the number of minima. Also, by the way, we will assume that for reasons of symmetry, the maxima will be as many as the minima. So if we count the maxima, it's okay. And if we want to know the total number of peaks, we simply multiply the number of maxima by 2, because the number of maxima will be the same as the number of minima. But since we are interested only in the positive peaks, we have to take care of the maxima. We have to count the maxima. And by the way, you can see that at these gaps, so for example here, at this gap when the function goes from the value 1 to the value 0, we have a maximum here. Similarly, when the function goes from 0 to 1, we have a minimum. So you understand the idea. So at t2, the function has the gap here, so it goes from 1 to 0. It decreases. And we might take the derivative once again of this step function. So if we take the derivative of the step function u of x prime of t, what we get is the Dirac delta of x prime of t, and then we have to take the derivative of the argument, which is x double prime of t. like this. So it means that this function behaves like this. It will have a negative Dirac delta at this point, which is T1. Then it will have a positive Dirac delta because we go from 0 to 1, so it's increasing, and therefore here we have a positive Dirac delta at this point. Then we have another negative delta at this point, which is t equal to T2, and then you get the idea, right? So here you get another positive delta, here you get another negative delta, and so on and so forth. And you can see that the maxima will be as many as the negative deltas. And of course, the minima will be as many as the positive deltas. In general, if you continue this reasoning here and you consider the assumption that the number of maxima is equal to the number of minima, well, if we count these deltas, they will have to be as many as the positive deltas. And in particular, if you want the total number of peaks, you will have simply to consider all these deltas, both the negative and the positive deltas. And you can turn these deltas also into positive deltas. For example, if you consider this function, but in particular, instead of x double prime, you consider the absolute value of x double prime of t, right? And this function can be also written, and you can see that from here. Now, this function here will coincide with the same function here, but you have to turn the negative deltas into positive deltas, like this. And you will have a summation. You will have a summation of this kind. You will have a summation over j of the Dirac deltas of t minus t tilde j. So this one is t1, then you should change a little bit notation, because then you have t2, which should be this delta here, because now you're considering all the deltas. So we call this t2, or if you want, you might have tk here. I don't know. They don't have to be in increasing order. But if you want to think this in an intuitive way, then of course you might call this one T1, then you might call this one T2, then you might call this one T3, T4, T5, and so on and so forth. This was just for the sake of visualization, but it is just notation. Now that we have this formula, this was the formula that I wanted in order to start the subsequent derivation, in particular the total number of positive peaks, we can write it like that. So we have n tilde p plus, so this is the number of positive peaks per unit time. So if we want the total number of peaks, we multiply this by capital T, which is the duration of the signal. And then this is equal to 1/2 integral from 0 to t, and then we have to integrate this function, right? Because we know that this function is equal to the summation of the deltas. So when we integrate a delta, we get a 1. And therefore, if we integrate this function here, we will get the total number of peaks. But if we want the positive peaks, we multiply by 1/2. Because by assumption, we know that the number of maxima is equal to the number of the minima. So here I can write delta of x prime of t times absolute value of x double prime of t dt. And we can also rewrite the same integral. Instead of 0 to t, we can integrate from minus infinity to infinity. It's just the same. So in this case, the signal starts at 0 and it goes to capital T because that's the duration of the signal, but we can simply integrate from minus infinity to infinity. We know that the signal is defined between 0 and t, so this will reduce to the integral from 0 to t, but it's not so important. Now, instead of writing inequality here, let me consider the expected value. Now we want to consider the expected value of this. We want to find the expected number of total positive peaks. And this will be simply equal to, well, we have to use the joint distribution of these signals. We have x prime, x double prime, and in general we have to consider the joint distribution f x x prime x double prime. Now I will write it, but first let's write 1/2. Then we have this integral here, in general from minus infinity to plus infinity, but now let's rewrite it as integral from 0 to t. And then now here we have to integrate from minus infinity to plus infinity. We have a triple integral like this. Now I will show you what kind of integral we have. We still have the same function here, delta of, now instead of x prime of t tilde and x double prime t tilde, I'm just going to write x prime, and then here I'm just going to write x double prime, because now here we have a distribution f x x prime x double prime, so this is a joint density. It's in this case we don't have only two variables, we have three variables: x, the signal itself, the derivative of the signal, and the second derivative. And this is a function of x, x prime, x double prime, and in general this might also depend on t if the distribution is non-stationary. And then here we have to consider the differentials. So we have dx, dx prime, dx double prime, and dt. So this dt belongs to the integral from 0 to t here, which could also be an integral from minus infinity to plus infinity, but I wrote it like that. And now we can integrate over x prime here, because we have this Dirac delta, which makes the integration quite simple. So if I integrate over x prime first, I will get rid of the Dirac delta, and instead of x prime here I can evaluate this density at 0, and I can get rid of this differential. And I also have to cancel one integral sign here. And then let me also change the notation a little bit. So instead of using x double prime as the variable of acceleration, I'm going to use c. Here I'm also going to use c, and here I'm also going to use c, and then I'm going to use a instead of x. So let me call this a, let me call this a. This is just notation. And then now I'm going to assume that this density here does not depend on time, so it is stationary, which means that we don't have to consider a dependence upon t. Therefore, I can integrate over t, I can get rid of this integral, and therefore here I simply have to multiply by t. And also, finally, instead of integrating over c from minus infinity to plus infinity, I'm going to integrate from 0 to infinity. And for reasons of symmetry, I have to multiply by 2. So I will get rid of this 1/2. And I can also write the absolute value simply as the value itself, c, because c will be greater than 0 in this case, greater than or equal to 0. So basically what this means is that the expected value of np plus will be equal to the integral from minus infinity to plus infinity. Then we have an integral from 0 to infinity, c f of x, x prime, x double prime of a 0 c, and then here we have dc dA. But now if I integrate over a, then I will get the following integral from 0 to infinity of c. Then when I integrate this distribution here over a, I'm going to get the distribution f x prime x double prime, because I eliminate the variable a. So This function will be a function of 0 for x prime, and c here for x double prime, dc. That's how I can write it. And if x prime and x double prime are Gaussian, so it means basically that the variable x, the signal, is Gaussian. So if the signal x is Gaussian, also its derivative will be Gaussian, and also its second derivative will be Gaussian. This is quite intuitive. I will not delve into the details of this, but let's assume that x prime and x double prime are just Gaussian variables. And as I said, it's quite intuitive. If you write x as a series and then you take the derivatives, you will quite easily understand that also the derivatives of x are Gaussian. Because remember that the randomness in the signal, x or x prime or x double prime, can be found in the phases of the signal, and the phases are uniformly distributed. So you will see that it will hopefully easily motivate the fact that those variables are Gaussian if the signal x is Gaussian. And now we have a function, we have a formula for f of x prime, x double prime, knowing that x prime and x double prime are Gaussian. We can use the joint distribution, and you have to set the first variable equal to 0 and the second one equal to c. You can rewrite this as 1 over 2 pi sigma x prime, which is the standard deviation of the variable x prime, and then you have sigma x double prime, and then here you have the square root of 1 minus a scalar r squared, where this scalar represents the degree of correlation between x prime and x double prime. Then here we have e to the minus c squared divided by 2 sigma x double prime squared, 1 minus r squared. And now we can show that x prime and x double prime are independent, which will mean that r is equal to 0. So if r is equal to 0 for two Gaussian variables, then we know that those two variables are independent. And in order to show that, we have to show that the expected value of x prime, x double prime is equal to 0. And how can we do that? Well, let's rewrite this expected value like this. This is the expected value of x prime, and then here we have the derivative with respect to time of x prime. But this can be written as the expected value of 1/2 derivative with respect to time x prime squared. And now we can take this derivative operator outside of the expected value, so that's just a linear operator, and we can put the derivative with respect to time outside of the operator. So we can write that as 1/2 derivative with respect to time of the expected value of x prime squared. But what is this expected value here? Now, we have implicitly assumed earlier that the signal x has a zero mean, which means that also the derivative will have zero mean, and also the acceleration will have zero mean. So this is quite important. It didn't say that, but it's also implicitly assumed here in this formula for x double prime, because you can see that only c appears. But anyway, now here this expected value will be equal to the variance of x prime, so it will be sigma x prime squared, the square of the standard deviation. But now we have the derivative with respect to time of the standard deviation of x prime. We are assuming that these signals are stationary. We have assumed that earlier. So this will be 0, because this characteristic, the standard deviation, does not vary with respect to time if the signal is stationary. So this will be 0, which means that r is also 0, and now we can simplify this formula. we can set r equal to 0. So this will be equal to 1 over 2 pi sigma x prime, sigma x double prime, e to the minus c squared over 2 sigma x double prime squared, like this. And now we can use the formula here and do the integral and carry out the integration. And the integration is quite simple, quite easy to carry out. And what you will get is simply 1 over 2 pi sigma x double prime divided by sigma x prime. And this is the result that we obtain. In general, if r were not equal to 0, you will get also the square root of 1 minus r squared in this result. But since we know that r is equal to 0, well, there's no need to complicate things. So this is where we stop for this lecture.